Einstein was the man who gave birth to quantum mechanics, but he was also its most passionate opponent. He once declared, "God does not play dice with the universe." So why did the world's smartest man refuse to believe in the very theory that modern physics depends upon when physics faced its greatest crisis? At the end of the 19th century, physics seemed almost complete. Newton's laws explained motion with mathematical precision. Maxwell's equations described light and electromagnetism beautifully. And the universe appeared to operate like a vast, predictable clockwork. Scientists believed they were just filling in the final details of a fundamentally understood reality. Then, strange experimental results began appearing that refused to fit this tidy picture. Light sometimes behaved like waves, creating interference patterns that could only be explained by wave motion. But other experiments showed light acting like particles, striking surfaces in discrete packets of energy that seemed impossible to reconcile with wave behavior. In 1905, Einstein himself provided the solution that would eventually shatter his own worldview. His explanation of the photoelectric effect demonstrated that light could carry energy in discrete bundles called photons, behaving like particles rather than continuous waves. This insight earned him the Nobel Prize and laid the foundation for quantum mechanics. The profound irony is that Einstein helped birth the very theory he would spend the rest of his life trying to disprove. He opened a door to quantum reality, then spent decades trying to close it again. His early success in explaining light's particle nature made him one of the founders of quantum theory. But the implications of that theory would soon become more than he could philosophically accept: the rebellion of reality itself. As younger physicists like Niels Bohr, Werner Heisenberg, and Max Born developed quantum mechanics throughout the 1,920 seconds, they uncovered principles that seemed to violate everything humans intuitively understood about reality. Their mathematics suggested that particles could exist in multiple states simultaneously until observed that the act of measurement fundamentally changed what was being measured, and that the universe operated according to probability rather than absolute laws. These ideas represented more than just new physics. They constituted a complete overthrow of classical reality. According to quantum mechanics, an electron didn't have a definite position or velocity until someone measured it. Before measurement, it existed in a ghostly superposition of all possible states, only collapsing into a specific reality when forced to by observation. For Einstein, this quantum picture was nothing short of an intellectual catastrophe. The idea that reality depended on observation struck him as absurd. In one of his most famous challenges to quantum theory, he asked, "Are you telling me the moon isn't there when I'm not looking?" The notion that the universe only became real through the act of measurement violated his deepest convictions about the nature of existence. Einstein's resistance wasn't based on mathematical incompetence. He understood the quantum formalism perfectly. Instead, his opposition stemmed from a profound philosophical commitment to the idea that reality should be objective, deterministic, and independent of human observation. The quantum universe seemed to make reality contingent on consciousness, transforming physics from a description of objective truth into a catalog of measurement probabilities. The greatest debate in physics. The conflict between Einstein's classical worldview and quantum reality reached its peak during a series of legendary debates with Niels Bohr at the Solvay conferences between 1927 and 1930. These weren't merely academic discussions, they were philosophical battles for the soul of physics itself. Einstein approached these debates like a master chess player, devising increasingly sophisticated thought experiments designed to expose contradictions in quantum mechanics. He would propose scenarios where quantum theory seemed to lead to paradoxes or impossible conclusions, hoping to force his opponents to acknowledge the theory's fundamental flaws. Bohr met each challenge with equal brilliance, demonstrating time and again that Einstein's objections were based on classical assumptions that simply didn't apply to quantum systems. When Einstein would ask which path a particle took through a double-slit experiment, Bohr would respond, "There is no answer to that question." The moment you ask which path, you've already changed the nature of the experiment. The famous exchange that captured the essence of their disagreement occurred when Einstein declared God does not play dice with the universe. Bohr's reply became equally legendary: "Stop telling God what to do." This wasn't mere wordplay. It represented a fundamental clash between two incompatible visions of how the universe operates. Einstein believed that the universe must have underlying order and causation, even if humans couldn't always perceive it. Bohr argued that the universe simply operates according to probability, and our failure to find classical causation reflected the limits of classical thinking rather than the incompleteness of quantum theory. The fear behind the genius. Einstein's resistance to quantum mechanics wasn't rooted in scientific conservatism or intellectual stubbornness. Instead, it emerged from his deepest fears about what quantum theory implied for human understanding and cosmic order. He wasn't afraid of the mathematics, he was afraid of what the mathematics suggested about the nature of reality itself. The quantum universe threatened everything Einstein held sacred about scientific inquiry. If reality was fundamentally probabilistic rather than deterministic, it meant that complete understanding of the universe might be impossible in principle. If the act of observation changed what was being observed, it meant that objective reality, reality independent of human consciousness, might not exist at all. Einstein spent decades searching for hidden variables underlying deterministic mechanisms that could restore classical causation to quantum phenomena. He believed that quantum mechanics, while mathematically successful, was incomplete. Somewhere beneath the probabilistic surface, he was convinced, lay a deeper layer of reality that operated according to classical principles of cause and effect. This search was motivated not by scientific evidence, but by philosophical necessity. Einstein needed the universe to be comprehensible in classical terms, because incomprehensibility threatened the entire scientific enterprise. If humans couldn't, in principle, understand how the universe really worked, then what was the point of scientific investigation? When experiments chose sides decades after Einstein's death, sophisticated experiments finally tested his hidden variable theories against quantum mechanics directly. John Bell's theorem, proved in 1964, showed that any theory based on hidden variables would make different predictions than quantum mechanics for certain carefully designed experiments. When physicists like Elaine Aspect actually performed these tests in the 1,980 seconds, the results were unambiguous. Quantum mechanics was correct, and Einstein's hidden variable theories were wrong. The universe really did seem to operate according to the strange, non-local, probabilistic principles that Einstein had found so philosophically unacceptable. These experiments revealed something even more disturbing than Einstein had imagined. Not only was reality probabilistic rather than deterministic, but quantum entanglement showed that widely separated particles could instantaneously influence each other in ways that seemed to violate the principle that nothing travels faster than light. Einstein had called entanglement spooky action at a distance and dismissed it as evidence that quantum theory must be incomplete. But the experiments showed that this spookiness was real. The universe actually did contain connections that transcended classical notions of space and time. Reality was even stranger than Einstein's worst fears had suggested. The beauty of being wrong. The story of Einstein's resistance to quantum mechanics reveals something profound about the relationship between scientific genius and philosophical commitment. Einstein wasn't wrong because he lacked intelligence or mathematical ability. He was wrong because he was loyal to a vision of cosmic order that was too beautiful to abandon. His conviction that God does not play dice reflected a deep aesthetic and philosophical commitment to the idea that the universe should be comprehensible, orderly, and beautiful in classical terms. When quantum mechanics suggested that reality was fundamentally strange and counterintuitive, Einstein chose to trust his philosophical intuitions over the experimental evidence. This choice, while ultimately incorrect, played a crucial role in the development of physics. Einstein's persistent challenges forced quantum theorists to refine their arguments, develop more sophisticated experiments, and explore the deepest implications of their theory. His refusal to accept quantum mechanics helped make quantum mechanics stronger. The irony is that Einstein's opposition to quantum theory embodied the same spirit of questioning that had made him great in the first place. Just as he had challenged Newton's assumptions about space and time, he now challenged the quantum assumption that reality was fundamentally probabilistic. His greatness lay not in being right about everything, but in having the courage to question everything, even his own previous insights, the universe that refuses to be tamed today. Quantum mechanics forms the foundation of our most advanced technologies: lasers, computer chips, MRI machines, and countless other devices depend on quantum principles that Einstein found philosophically unacceptable. We're even beginning to build quantum computers that exploit the very superposition and entanglement effects that Einstein dismissed as impossible. Yet, in another sense, Einstein's concerns remain as relevant as ever. We still don't truly understand why quantum mechanics works or what it means for the nature of reality. The measurement problem, exactly how and why quantum superpositions collapse into definite states, remains unsolved. The relationship between quantum mechanics and consciousness continues to puzzle philosophers and physicists alike. Einstein's debate with Bohr wasn't just about physics, it was about whether humans can ever truly understand the universe they inhabit. Einstein believed that complete understanding was possible and necessary. Bohr suggested that complete understanding might be neither possible nor necessary, that successful prediction and control might be enough. This philosophical tension continues to drive physics forward. Every new quantum experiment, every advance in quantum technology, every attempt to reconcile quantum mechanics with gravity represents a continuation of the conversation that Einstein and Bohr began nearly a century ago. The wisdom of principled doubt. Perhaps the most important lesson from Einstein's quantum struggles isn't about physics at all. It's about the value of principled disagreement in advancing human knowledge. Einstein's refusal to accept quantum mechanics wasn't mere stubbornness. It was a commitment to questioning even the most successful theories when they violated his deepest convictions about how reality should work. This willingness to stand against scientific consensus, even when that consensus was based on solid experimental evidence, exemplifies the kind of intellectual courage that drives scientific progress. Sometimes being wrong about specific details is less important than being right about the need to keep questioning. Einstein's resistance to quantum mechanics forced the physics community to confront the full implications of their theory. His thought experiments and philosophical challenges helped reveal just how strange and wonderful the quantum universe really is. In trying to prove quantum mechanics wrong, he helped prove just how right it was. The deeper message isn't that Einstein failed when he opposed quantum mechanics, but that science advances through the creative tension between revolutionary theories and principled skepticism. Einstein's quantum doubts, like his earlier relativistic insights, remind us that the most important scientific advances often come from those brave enough to question what everyone else accepts as obviously true. Einstein once wrote, "The most beautiful thing we can experience is the mysterious." Perhaps his greatest gift to physics wasn't any particular theory, but rather his demonstration that even the most brilliant minds must remain humble before the magnificent strangeness of the universe. In his lifelong struggle with quantum reality, we find not the failure of a great scientist, but the success of a great questioner who never stopped demanding that the universe make sense even when the universe refused to cooperate.